And let's go to our whiteboard. And let me get things sort of scooted around here. I don't think you can see what I'm talking about here, but I have a taskbar at the bottom that's right in the middle, not in the middle, but right blocking a whole portion of the white page. So I got to move it down to the bottom. And then Ricky is in the way, of course. She's over here a little bit, so I'm going to scoot her over, and all of you, by the way. And then there's a taskbar for the whiteboard that's in the way, so I'm going to move it up and out of the way as much as possible. And then move the whiteboard as far away from all those boards as I can, so I have maximum white space. That may be the only part you can actually see me moving. I don't know. Okay. So any questions on anything we've done so far? I guess since we've got 3 of the 4 of you here, let's go on and do another paid political announcement. I wanted this one on the recording, so Jemanuel, who's not here, will also have a chance to hear it. Okay. Now this, obviously my best class ever. Research papers. Half of you. 2 out of the 4 have turned in a research paper. Please, folks, Tuesday is technically the last day to receive it without losing points. So please try to get me the research paper as soon as possible. Okay? So, now, if you don't see your grade on Blackboard, I'm behind on Blackboard, so don't sweat that. 2 out of the 4 of you have turned in research papers that I've noticed so far. If you turned it in the last 24 or plus or so hours, I may not have seen it because I didn't have much time to make copies to print last night. So I'll catch up anything. You 3 have turned in your first test. The one who's not here has not. Okay. Ugh. The second test, I believe a couple of you have turned those in. I don't have the grades on Blackboard yet, but thank you for turning those in. But the second test, I'm still missing at least 1, I think 2. I will have to go check. The third test, I'm trying to think if anyone's turned that in. Okay, please, I think so. I think someone did turn in the third test. Okay, I don't have it graded yet. I have a stack of papers somewhere here, right here, that I was grading between classes. These have all come in the last, I'd say, day or so. Maybe a little bit longer than a day, but I mean, they've been piling in suddenly at the end. Okay, now, so there's that. The fourth test is the one on the chapter we're doing now. I will be giving you that test next Thursday, 1 week from today. So what we cover today, what we cover on Tuesday, and we may cover just a little bit more just to make sure you have everything covered on the test. That will be on Thursday, and then I'll give you the final. And here's going to be the setup, folks. Please try to get, as I said, research papers if you haven't done that. First test if you haven't done that. Second test if you haven't done that. Third test if you haven't done that. Try to get those in this weekend if possible. Okay? Especially the research paper by Tuesday. Otherwise you're going to start losing points on it. The other tests, get them in as soon as you can. Now, and I think I said this maybe last time we met. Don't wait until you get them all done. If you got something done, get it to me. And then if you get the next thing done, get it to me. That gives me the optimum time to be grading them. Okay. Because we're going to hit a crunch next week, and that crunch is going to be crunching on me pretty badly. If everything comes in next week, that's going to be really hard to get everything graded. So get it to me as soon as possible. Now, I contribute to the crunch in one way because we're going to be out of town this week, okay, this weekend. And that way I won't be able to print anything that comes in after Friday morning. So if you can get me anything today, I can take it with me. I can grade while I'm out of town, but I won't have access to a printer because our internet is pathetic. I won't be able to put grades on Blackboard. The internet over there is pathetic. It's slow and it's unreliable. And every system we use here at the college is is a bandwidth hog, and so I just don't think I'll be able to get anything to work well there, and I won't even have a printer. So please try to get me what you can. If you got anything almost finished today, get it to me today if at all possible. Okay, we'll be leaving very, very early tomorrow morning. My wife's a infectious disease epidemiologist. She wants to get on the road as early as possible, so when we do have to stop and get gas, which we will be early in the day, and few people will have been in the place, restrooms and that kind of stuff. We touch the minimum that we can, get back out, hand sanitizer, the whole works. So just to minimize that. Then when we get to the farm, we're not going to be around anyone. Some of my siblings will show up, but we're only going to meet them outside. They're not coming in the house, okay? We'll sit on the porch, or we'll be working in the yard and talking with them then. Okay, so anyway, that's this weekend. We come back very, 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 very early Monday morning. I've got an 11:30 class. I'll get back hopefully before it starts. We're going to leave extremely early in the morning, so therefore when we do have to make that stop for gas, we can get that done with minimal exposure to anybody and then hit the road. We're eating in the car as we drive. We're doing everything. Basically both mornings it'll be just breakfast, because we'll get home in time for lunch, so and get over there in time for lunch. So late lunch, but still get there. So I will be out of pocket, so don't expect me to respond to things quickly this weekend. But once I get back, I'll be in class the rest of the day on Monday, and then Tuesday morning we'll be in this class, so there won't be a lot of time for me to respond to much then. But then Tuesday afternoon, I hope to be able to start getting caught up on grading. So get me as much as you can now so I can grade over the weekend. I'm hoping we have a little bit of rain time, so I won't be working the whole time, and we'll be able to come inside and do some grading. All right. Any questions? How we're going to wrap up the term? And then when I do give you the final exam next Thursday, this 1 week from today, please try to get it into me as soon as you can. It'll be a fairly easy test, I think, to do. Fairly short, not all that long. So if you can get it to me Thursday, that would be wonderful. Friday would be good. Saturday is okay. Please get it to me by Sunday of not this weekend, but the following weekend, because grades, I think we have to have grades in by noon on Monday. And I can't receive and print and grade and average everybody's test on Monday morning. I can't do it. There's no way. So I'll have to give a bunch of incompletes if I don't have everything by Sunday, and the earlier the better. Now next weekend I'll be home. I'll be able to check emails. I'll be able to print. I'll be able to grade. So please get me as much as you can, as early as you can, this weekend, next week, and then next weekend. Okay? Any questions? Is that fairly clear? I know I ramble on and on and on. All right, then let's hit linear algebra. Okay. We're in Chapter 4, Vector Spaces, and the 4.2, the title of this section is, guess what? Vector spaces, okay? I guess they're focusing on vector spaces here, okay? We had done everything up through page 162. On page 163, top of the page, we were going to do example 5. Now, for those who weren't here last time, when we're talking vector spaces now, vector can mean a lot of things. It doesn't have to be a directed line segment anymore, okay? It can be a matrix or a set of matrices. It can be equations. It can be functions. It can be polynomials. It can be a whole bunch of things, okay? And this example is going to be continuous functions. So this is a vector space of continuous functions. No directed line segment vectors involved at all, okay? Now, if you happen not to have the text, you can go to larsonlinearalgebra.com and see an interactive version of this type, maybe this exact example, Okay, so here's the setup here. Maybe I better keep my book in the lap for just a moment here. Now here's where we begin. Let's see, they're going to title this space C, capital C. Now its domain of this set happens to be from negative infinity to infinity. Now they don't all have to be. You can have spaces that are much smaller than this, okay, but this one happens to be that. And sorry. I'm so sorry. I've had throat problems all morning. Partly because we had to get up early this morning, get my wife's car to the shop. Somebody hit her right rear door handle in the parking lot and broke it. And they got the part in earlier this week, yesterday or the day before. And today was the only day we could get it there so they could work on it because of my teaching schedule was so wacko. So we got up very early this morning to get it to them on time. And they were already packed jammed. That was just amazing. Got home, so my whole morning has been kind of out of kilter. Usually I try to rehydrate in the morning. I haven't had the chance this morning, so it's kind of crazy. Okay, so here's C. It's the set of, and actually I'm going to use some symbology. Sets are usually denoted by things in braces. Set of all real valued continuous functions thing is such a pain in the neck. Functions. I'm abbreviating like crazy. Defined on the entire real number line. That's why it's minus infinity to infinity. And I'm just going to say R, real number. That means this thing here. That's what your set is. Now, for those who weren't here before, a vector space, every vector space is a set. It's a collection of things. They don't have to be vectors in the classic sense. This happens to be the things are real valued continuous functions. Okay? Defined anywhere on the real number line. Okay? That set consists of all polynomial functions and all other continuous functions on the real number line. Sine x would be included. Cosine x would be included. 1 over x, not included. Why? Not defined as x equals 0. It has to be all real value continuous functions defined on the real number line. And what's more, the 1 over x is in the third quadrant and in the first quadrant. Not continuous. Remember, it said all real value continuous functions defined on the real number line. Sines and cosines, no sweat. Log, no, not there either. Log is only defined for positive numbers, so it would not be included here. These are all real valued continuous functions defined on the entire number line. Tangent function, would that be included? No, because the tangent function has vertical asymptotes. So it's discontinuous and not defined on those vertical asymptotes. Okay? So most of you, or a lot of your rational functions, if they have any place where the denominator would become 0, not defined. Okay? So these are all the real value continuous functions defined on the entire real number line. Okay? Like I said, it contains all polynomial functions. They're defined everywhere. All other continuous functions on there, sines and cosines, e to the x, yeah, perfectly fine. Defined everywhere on the real number line. Okay? Now, remember, when we're talking about vector spaces, you have to give what your rules for addition of those vectors, okay, those continuous functions in this case, and the rule is just what you would expect, that if you have f plus g, f and g are any two functions that are in that set defined for the variable x, the definition of their sum is exactly what you've always learned it to be, f of x plus g of x. And if those are continuous real valued functions, that works for every one of them. Okay? Now, how about scalar multiples? Just like we normally define it, c times any one of those functions defined on the real number line. Their standard definition for this will work here, and that's just c times f of x. Just like you would normally expect it to be. So, for every vector space, you have to have defined what the sum and the scalar product of those vectors would be. And there they are. Straightforward. Okay? Now, what you have to show is that continuous set of continuous functions is not just a set of continuous functions. We know it is. Is that also a vector space? Okay? Now remember what is required to be a vector space. Okay? Flip back one page and there's those 10 rules we've had over and over and over again. Well, first place, the sum of any two vectors here, just as defined here, is also a real value function on the entire real number line. So it's closed. It doesn't matter which order. F plus g is the same as g plus f. That doesn't matter. So that's good. First two are covered. If you had three of these functions, also an r of x or whatever you wanted, h of x, okay, whatever the next function was, all three of those are real value functions. You add two of them together, then add the third. Do you get the same thing if you add the first to the sum of the second and third? Yes. Functions add that way. So that works. Does this vector space have a zero vector? That's essential. Well, yes. All real value function, continuous, defined on the real number line. The zero function, that's the horizontal x-axis, is defined everywhere on there. Every element in that is zero. Okay? So sure enough, the zero function does exist, and if you add any other function to the zero function, you get that any other function. It doesn't change it at all. And the last one in this addition part is for every function there has to be another function that would be, if you add that function, the original function to the other function, you have to be able to get a zero function out of it. So yeah, all real value functions add their opposites. Okay, there is an opposite there. It's also in this set. Add them together and you'll get the zero function. Okay, scalar multiplication, this rule right here at the bottom, that says it's in the vector space, and it is. It's in that space. Every multiple of any function is also a real value function in that space. And if you multiply c times the sum of any two functions in that space, that would be c of f plus c of g. By this rule right down here, yes, it does work. If you had two scalars, c plus d, multiply them by some function f that's in that space, sure enough, that would be cf plus df. Okay, no problem. If you had two scalars, c, d, multiply d by f, that's in that vector space, that's in that set, and then multiply that by C, and that's in the set, okay? And guess what? That's the same as multiplying C and D together and then multiplying that by your function. Works across the board, okay? And then also, for any function in that space, in that set, you multiply 1 times that function, you get that function again. So there is a scalar identity, additive identity element, the number 1, okay? So sure enough, it meets all the requirements of a vector space. It's a set, meets all the requirements, so therefore it is a vector space, okay? Now, they give near the bottom of the page there a summary of your important vector spaces that you know are always vector spaces. First, the real number line, because it follows all the rules of addition, subtraction, multiplication, division, except of course you can't, well, division isn't included. Any number multiplied by a number on there is also going to be a number on that line. Okay, that's good. All the things are met. R2, all ordered pairs, set of all ordered pairs in a plane, they are a vector space. Set of all points in space, 3 dimensions, that's a vector space. The set of all, and these are literally vectors, these are n tuples, are n, okay? If you had n independent dimensions, so you have n tuples, ordered n tuples, a sub 1, a sub 2, a sub 3, a sub 4, up to a sub n, b sub a, sub b sub 2, b sub 3, b sub 4, up to b sub n, all those, they are vector spaces, okay, set of all n tuples. Now, I'll just hit a button there, okay, sorry. All continuous functions defined on the entire real number line, we just did it, that's a vector space. All continuous functions defined on a closed interval a to b, where a is not equal to b, that's a vector space, okay? Now remember, the a to b defines your input, the x, okay? And if a function's defined there and another function's defined there, their sums defined there, their products, yeah, everything's defined on that space, okay? Set of all polynomials, that's a vector space. The set of all polynomials of degree less than some quantity n. We did less than 2, I believe it was, on example 4, degree 2 or less. You could do any, pick any number. 17, set of all polynomials of degree 17 or less is a vector space, okay? Set of all n by m by n matrices, that's a vector space. You add to m by n matrices, you're going to get an m by n matrix. You multiply a scalar by it, you're going to get a m by n matrix, okay? So those are all work. All square matrices, that's just where m is equal to n, those are all vector spaces, okay? Now, even though they contain things other than our classic vectors, your R, R2, R3, Rn, those are your standard vectors, ordered in tuples, okay? But continuous functions, polynomial functions, matrices of just about any size, as long as they're all the same size, those are, set of all those is, those are vector spaces. Now, going to page 164. You have seen the versatility of the concept of a vector space. For instance, a vector can be a real number. It can be an n tuple. Think a true vector with as many dimensions as you want. A matrix, a polynomial, a continuous function, and so on. So, why, if all these things can do it, why bother to define it? Several reasons, but the most important reason applies to efficiency. Now, this is a lot of blah, blah, blah. Once a theorem has been proved for an abstract vector space, you don't have to prove it for every vector space. If it works for any vector space, it works for all vector spaces. So that's what they're talking about here. You don't need to go back and prove them again and again and again just because you come up with a new vector space. Simply point out that the theorem is true for any vector space, regardless of the form the vectors have, whether they're matrices, polynomials, functions, or vectors, okay? Now, here is theorem 4.4. Now, all of you do have a book, right? So rather than write this down, well, I may write it down. Let me evaluate it. Let me first hold it up so you know what I'm talking about. I'm scared I'm going to drop that stylus. They're very expensive. So here's the theorem, 4.4. Okay? That's what I'm talking about on page 164. Let V be any element of a vector space, capital V. Now, again, we're going to use the same nomenclature as if they were really directed line segments. The book bolds it. I put an arrow over it, even though it may not be an arrow at all. It may not be a directed line segment. It may be a matrix, you know, but we're going to use that same terminology. Let little v, bold little v, or with an arrow over it. Let me go on and write it. Okay, I thought I could talk through it, but it's, again, too abstract. Okay, so let's do it. I can leave it on here. Okay. So, what we used to call a vector v, let me separate this. Okay, vector b, be any element of a vector space. Now I'm going to give this symbology like this. Any element of the vector space, capital B. Like capital C stood for continuous function, capital V stands for any vector space with the corresponding elements in it be little vector v's. Okay? And let C be any scalar. Now, if you were doing this for continuous functions where you let capital C be the vector space, then little c, bold little c's, or little c's with arrow over it, or a little c sub 1, little c sub 2, little c sub 3, those would be your individual functions. But then this c, scalar, that gets a little confusing. But we're not doing that now, so c is a scalar. Then these four properties are true. First, for any vector space, the number 0 multiplied by whatever vector that is, matrix, function, polynomial, whatever, this is going to produce the 0 vector in that vector space V. Again, that would be a matrix, a polynomial, or whatever. Okay, that's going to be true for all these, no matter what you're dealing with. Okay, number 2, if you have that any old scalar C multiplied by the 0 vector in that vector space, you're still going to get that 0 vector in the vector space. Okay, that 0 vector could have been a polynomial, 0 x to the n plus 0 x to the n minus 1 plus 0 x to the n minus 2. All the coefficients are 0. That's your 0 polynomial. Okay? 3. Just because V is a vector in a vector space, that makes these things true. You don't have to go back and prove them every time. Here's one. If, this sort of combines the two above, not quite, but it's sort of like it does. If you know that C times the vector V is equal to the 0 vector, you know that, okay? What does that tell you? That means that either C, the constant is the number 0, or V, the vector you're talking about, has to itself be the 0 vector. So it's kind of like, okay, 0 times a vector, any vector in that space is a 0 vector then. C times the 0 vector in that vector space will still be the 0 vector. So therefore, if you have a product, C times V, a vector, and you know the answer is the 0 vector, that means one of those first two had to be true. Either the C is 0 in the second one, no, in the first one, or V is 0, which is the second one. Okay? And then this is also true of every vector space. If you know it's a vector space, you can negate the vector V, and that will be the opposite of V. Okay, whatever that is, a polynomial, a matrix, whatever. If you multiply -1, the scalar -1, times whatever vector, matrix, polynomial, function, whatever it is, multiply that by -1, you'll get the opposite of that, which when you add it to the original V, you're going to get 0. Okay? Now, they take you through a proof of one of those. I've kind of talked my way through the proof on every one of them, so hopefully you can follow that. Now, they have another example of linear algebra applied, and this is basically dealing with springs. Basically, it's dealing with simple harmonic motion. And if a system has just 1 degree of freedom, like a mass on a spring that can only go up and down, then they give you a situation for that. And they identify what the natural frequency of that system is, and basically it's saying linear algebra can be applied with those kind of problems. I don't want to get into the nitty-gritty of it, but I'll let you read that. If you find something in there you feel like is reasonable paper topic, by all means do it. Now, it may have seemed to you that it seems like anything we came up with could be called a vector space. That is definitely not true. Okay? Now, here's a fairly simple set, which you know is a set, and with just a little bit of thinking about it, you realize it's not a vector space. Okay? Let's call capital I, now that's not to be confused with the identity matrix, but capital I is the set of integers. Well, that's not really the way to say it. Is a set of all integers. That's certainly a set of numbers, right? That is what capital I is, a set of all integers. That's supposed to be an N there. I don't know how it came out that. Okay? 1, 2, 3, 4, 5, -1, -2, -3, 4, -4, -5, 0. Those are your integers. That's a set. That's definitely a set. It's an infinite set. Is that a vector space? Well, you could start by adding all of them together. If you add them together, sure enough, that's going to be in the set of integers. Okay, if you commute them or associate them, yeah, that all works. Okay, in fact, everything, and 0 is in there. Okay, so everything on the addition side works, but remember on that multiplication side, scalar multiples, remember the requirement is for any scalar C, any real number C. The one the book uses, well, let's just use the number C to be 1/2. Well, let's multiply 1/2 by an integer. Let's just multiply it by 1. Guess what? That is 1/2, and 1/2 is not an element of your integers. So no, scalar multiplication does not work in the set of all integers. It works if the C is a whole number. Yeah, of course it would. But it doesn't work if C is a rational number or an irrational number, or remember, it can be any real number. So no, that is not it's certainly a set. It's a huge set. It's an important set. It's just not a vector space. Okay? That was example 6. Let's look at example 7. The set of all second degree polynomials. Okay? The set of all second, oh, didn't we do that one before? Okay, let's let this be, let P equal the set of all second degree, yeah, get out of there. Okay, second degree polynomials. We just said polynomials work here. No, if all polynomials, that works fine, and all second degree or less polynomials, that works fine, or 17th degree or less polynomials, that works fine. But how about all second degree polynomials? Can someone give me a second degree polynomial? Make up one. Anybody? How about that one? Is that okay with you? Okay, 2x squared, that sounds good. Any more? Okay, how about let's like plus x minus 1. 2x squared would have been fine too, but that's a second degree polynomial, right? Now, is this also a second degree polynomial? The pen is not writing well at all. I like 17 today for some reason. I don't know why. Is that a second degree polynomial? Of course it is, right? Okay. What if you were to add those two together? What does that give you? Say that again. No. It would give you 5x plus 16, right? Is that a second degree polynomial? No, it is not. It's a first degree polynomial. So the set of all second degree polynomials would not be closed under regular addition of polynomials. Set of all second degree or less polynomials, yeah, that's no sweat. You have to have the or less in there. Or you could say the set of all polynomials, no problem there. Set of all 14th degree polynomials? No. Set of all 14th or lower degree polynomials? Yes. Okay, you see why. Okay. Here's another one. Now this gets to be a little strange. And so I think I'll clear my screen. Those two are fairly straightforward. You can visualize those. Now this is where the strangeness comes in. Remember we said according to some rule you have to be able to add your polynomials and multiply scalar. You have to follow some rule. And so far we've been saying by the usual means. Well, what if you choose an unusual mean? Well, some of those may still work, but some of them may not work, and this is one example they wouldn't. So let V be and this is R2. I don't even like the way they're starting this. Okay, wait a minute. Here comes your manual, which means perfect attendance for today. Way to go, team. Unfortunately, I've lost my pen, so I can't mark the manual here. No, I can't. All right. Perfect attendance. Good to see. It's been a while, folks. Okay, and Jemanuel's here. Welcome, Jemanuel. All right. Now, I'll say this again for your benefit in case you might be tempted not to go back and listen to the YouTube video. Sorry, folks. This will be a repetition. Okay? According to what I've seen, now I may not have printed off everything in the last couple of days or so, but the last time I was printing stuff, which was sometime yesterday, I couldn't say I got everything printed yesterday. Just in the last day or two, I've received that much stuff in. Okay, so I'm behind on grading. And I'm probably a little behind on printing. I'm almost certain that Aaliyah sent me something yesterday that I didn't get a chance to print because I saw it in my email, but I didn't have access to a printer, and then I never got back to it again. So I know there are some of you have sent some stuff I haven't printed, but there's a lot of stuff here I have printed that I haven't graded. But I know there's stuff out there that hasn't been turned in yet. Okay, I don't know how much for sure, but I know there's some. So if you haven't submitted a research paper yet, please, this weekend, get that finished. Send it to me. If you've got it almost finished and can send it to me today, send it to me today. Send it to me tomorrow, Saturday, Sunday. Okay, now, Jemanuel, I was telling the others, I'm going to be out of town this weekend. We've got to make a trip over to Georgia. We have property over there that I inherited that we've got to do some maintenance to. And all this wonderful rain we've been having is wonderful, except it's making grass grow like crazy, and we've got to go take care of some of that. Okay, so we got to be out this weekend. And over there is way out in the country, not good internet at all, so I'm not going to be, and we won't even have a printer there, so I won't be able to print, and I hope to be able to get some of the grading done. I'm hoping for a little bit of rain time and downtime in the evening so I can get some grading done. But always my siblings come to see me when I show up there. They all live on the farm. We're the only ones that don't. So when we come in, they all come to see us at some time or another. And they won't do it all at the same time either. So it's going to be hard to grade while they're there, but we'll try to squeeze in some time. Okay, so anyway, get me the stuff this weekend, even though I can't print it. I want to get everything that's been done so far. Research papers, test 1, test 2, and test 3. All 3 of those have been given to you. Okay, try to get them in, especially the research paper, by Tuesday. Okay, and the others as soon by Tuesday if possible, but as soon after Tuesday if not possible. Because on Thursday I'm giving you the final exam. That'll be just a test on chapter 4, what we cover in chapter 4. Okay, now you will only have Thursday, Friday, Saturday, and Sunday to do it. I've got to have them all in by Sunday. I'd love to have them all in before Sunday, okay? So I can grade them by Sunday, get the grades in Blackboard, and then get the grades submitted by noon on Monday. I think that's our deadline. So please get me everything you can next week. And then once I give you the last test, the chapter 4 test, get that done as soon as you can. I don't want you having 3 or 4 tests out there that you haven't completed and you're having to do them all in one weekend. Get them done this time so you can have next weekend to work on the final. Okay. Also, have y'all seen anything about student course evaluations? I haven't, but I may have missed something. Have any of you seen anything about student course evaluations? No, I haven't either, so they may not be doing it this summer. I know they do it every fall and spring. I thought they tried to do it every term, but it looks like they're not going to do it this term. So that's going to be fine, okay? So I guess that's it. Try to get everything that's been assigned so far turned in as soon as possible. Today, if possible, the weekend, if possible, early next week for sure, because at the end of the week, I want you only to have that one last test so you can get it done in the basically 3 days you'll have, 3.5 days. I'd love to have them all in before Sunday if possible so I can grade them on Sunday. Okay? So, let's get back. We're in Chapter 4, Vector Spaces, and 4.2 is also named Vector Spaces. Okay? We're just getting ready to do example 6, which is a really strange example. And there it is. Just lost the pen. It's a black pen, so it doesn't show up well on anything. Okay. So here we have V is the vector, is a set of all ordered pairs of real numbers. Now, on the earlier page we said, I just want to remind you of this. If you flip back one page, it said, the summary below lists some important vector spaces frequently referenced in the remainder of this text. The operations are the standard operations in each case. That little sentence there is so important. Your standard operations for vector addition, remember vector can stand for any kind of thing, and scalar multiplication. As long as the standard operations are used, all these are vector spaces. This one, however, looks like one of the vector spaces, except it's a set of all order. It is a set, and this is R2, and this is the set of all ordered pairs of real numbers. It's exactly what R2 is, all ordered pairs of real numbers. I'm just going to put R for real numbers, with the standard operation of addition, so that's okay. Standard operation of addition. Now this is bizarre. I admit I find it bizarre. But with the non-standard operation of scalar multiplication to be this: C of any ordered pair, x sub 1, x sub 2, is now going to be, here is the definition for how you do that. It's going to be the ordered pair Cx sub 1. Now the standard one would be comma Cx sub 2. But this non-standard definition says every time you do that, the second element is going to be 0. Okay? Now, that is the set that we're dealing with. If I can get the pen to... Come on, pen. Where are you? There you are. Okay. Yuck. I hate this thing. Okay. There is a set. Okay? They're saying show that this is not a vector space. Wait a minute. Let's go back and look at the 10 requirements for the vector space. First, it's 2 pages back. If you add u plus v that's in this vector space, then the sum of that is supposed to also be in the vector space. Well, sure, it would be. Okay, no problem there. The addition, in fact, everything with addition is going to be fine because that's standard for the addition. Okay? Now, let's look at the scalar multiplication. Cu also has to be in the vector space. Well, it is. Cx1 comma 0 is in that same vector space. Okay? It is. How about C times u plus v? Yep, that would work too. Okay? I'll write this one out for you. This sort of shows how it is. This is number 7. Okay? C times u plus V. Okay? Now that would be C times U1 plus V1, comma, U2 plus V2. And according to this definition of scalar multiplication, that would be C U1 plus V1, comma 0. That's how you do scalar multiplication with this non-standard definition. Well, what would that be? That would be C U1, comma 0 plus CV1, comma 0, which would be CU plus CV. I forgot to put my arrows over. I'm sorry about that. Over the components you don't have to put it, but on the vectors you do. Yeah, that works. Okay? And you can do the next one too. C plus D times U. That would be C plus D times U1 V1, U1 U2. When you multiply them, that would be C plus D U1, comma 0. And that would be C U1 plus D U1, both comma 0. Yeah, that works. Okay? How about that next one? CD times U. That works too. But that last one, let's take a look at the last one. The very last one. 1 times U. Okay? Yeah. What would that be? That would be 1 times U1, comma U2. And when you multiply any scalar by a vector, you should get U1, according to this rule, comma 0. And the question is that the vector U? And the answer is no, it isn't. The vector U is this vector, not that vector. But the 10th rule said 1 times U must be U. Well, it isn't with this rule for scalar multiplication. That one rule boots it out and says, no, this is a set, perfectly good set, it's just not a vector space. Okay? Now, I went probably beyond the call of duty there, but that is indeed what they get. They use just a very specific one. They use the vector 1, 1. I use the general one, U1, U2. But by their rule of multiplication, that would be U1, 0. And that's not the vector U. Okay. So, now, they do a little statement at the bottom. Do not be confused by the notation used for scalar multiplication in example 8. In writing C x1 x2 equals C x1 comma 0, the scalar multiple is defined to be that in this thing. So to me, weird, stupid, oblique example. But maybe you run into things like that. I don't know. It seems like they made up something crazy. And of course it came out crazy. Well, that does finish 4.2. Homework exercises here would be any of the odds 1 through 5. They should all be at calcchat.com. Any of the odds 7 through 11, they should be at calcchat.com. Any of the odds 13 through 35, a whole big passel of those, they should all be at calcchat.com. Any of the odds 37, well, try to do 37, okay? Then 39 is a proof. You can do that if you would like. That all these should be at calcchat.com. 41, you could try that one. It should be at calcchat.com. 43 is a proof, but they don't say a proof, but that's what they're asking you to do. You can do that one. Now the mass spring system, this would be more like that linear algebra applied. You can take a look at that if you'd like. 47 is another proof. You can do that if you like. 49 is a true false with 3 pieces, so you can do that if you'd like. Then 51 is another proof. You can do that if you'd like. That's up to you. All those odds should be at calcchat.com. Now, we're moving now into 4.3. Now, I don't know if you're feeling like you may have been cheated this summer. I think you could legitimately feel that because it's supposed to be a 10-week term. Summer term at Lawson has always been a 10-week term. And I think I explained this to you before, but I'll do it again in case some of you weren't here. This summer, and this isn't just Lawson, I think it's everywhere in the two-year college system, or the vast majority of the two-year college system schools are having a weird summer, not just because of COVID-19 and being virtual and online and all that kind of stuff. There's another weirdness here, and that's the fact that the administration down in Montgomery had allowed this ancient package to be the operating system for as many colleges as wanted them, and Lawson opted for that. It was called the Alliance system. It was really a sorry old system to begin with, but it was really out of date and not very flexible, but everybody knew it and understood it and dealt with it. But Montgomery said this summer everybody has to change to the system they chose, everybody, and that's called the Banner system. So the whole college is going to a completely new operating system. Now, if any of you have registered for classes for the fall, you know things are different now. They were the same or very similar up until last week. Okay? Or this week, I guess it was, this week. Starting this week, everything has to be done on Banner. Okay? Well, guess what? The end of this month, July 31st, Alliant dies. Okay? We cannot do anything in Alliant anymore. Meaning, 1st of August, everything is Banner. Well, guess what? We've been doing the whole term in Alliant. We've been doing everything in Alliant, except like this week, change the registration in Banner. But that's for next term. Everything to do with this summer has been Alliant, and we have to close it out before the end of the month. So that's why grades have to be in by 1 week from Monday, because let's see, I don't have it in my head. Today's the 16th, Friday's the 17th, Saturday the 18th, Sunday's the 19th, Monday is the 20th. The next Monday is the 27th. Everything has to be in by the 27th because on the 31st, Alliant dies. So y'all are being cheated out of a week and a half of your tuition dollars. Okay, sorry about that. Now, one thing they did, and they did it almost by mistake, they made the classes too long. So in reality, we've almost done what we would have been able to do in a 10-week summer right now. The reason I say this, I just moved, and this isn't quite true. Last spring, we only got to the page we're going to start right now, okay? And the reason was because of COVID-19. We had to go off campus. We had to start doing virtual classes. We didn't have the technology for it. We didn't have the procedures for it. For instance, the computer that I had from the college died. They had to get me another one. They got me this computer, but it wasn't functioning. I couldn't even get into it. So they had to come get it, take it back. So I was using iPads. I was using just about every. My wife resurrected an ancient computer here, put a new operating system on it, And I taught from that for a while until they got this computer fixed. So it was a terrible end of spring term. I don't know if it was at your school, but it was here. So we didn't get but through the page we're starting right now done last spring. So guess what? Y'all are getting more than we did last spring. But last spring was, again, an unusual term. You still won't be getting as much as we would have been able to get had they given us a 10-week term. I'm sorry about that, but let's get as much as we can. And I've been talking too much. So let's move on to 4.3, subspaces of a vector space. Whoa, what do we mean here? Well, remember, a vector space, vector space is a set. Okay? Now, if you've done any set theory at all, fiddling around with it, playing with it back in your lower grades anytime, you know that you have subsets. Okay? And usually a subset is also a set. Okay? Well, a subspace is certainly a subset of the vector. Wait, I'm sorry. Let me back this off. A vector space is a set, so you can have a subset of that set, but that's not always a subspace. Okay, so it's little nitpicky of terms here, but here's what we're talking about. In many applications of linear algebra, vector spaces sometimes occur as a subspace of a larger vector space. For instance, we've already said the set of all polynomials is a vector space. Well, you may not want to deal with all polynomials. You may want to deal with all polynomials of degree 2 or less, which we've also seen is a vector space. Because that's a vector space, it's also a subspace of your original vector space, all polynomials. However, the set of all polynomials of degree 2 is a subset of your all polynomials, but it's not a vector space in itself because we proved it wasn't. So it would be a subset of the original set, but not a subspace of the original space. Okay? So that's what we're talking about. Sometimes we want to deal with a smaller space, but it'll still be a vector space. It's called a subspace of a larger one. Okay? Here's another example. You will see the solution set of a homogeneous system of linear equations in variables is a subspace of Rn. It won't be all the elements in Rn, but it will be a set itself. Now, here's a concept. I don't know if you remember this from set theory. Let's say you have a set. I'll just say it can be anything in there, not just spaces, sets. Anything in that set. Now, there is something they call the empty set. Okay, that would be a set with absolutely nothing in it. So this set has whatever it is in there. This set down here has absolutely nothing in it. Okay, that's called the empty set. Now, any set that has anything in it is a non-empty set then. Okay, so what we're talking about now is a non-empty set, subset of a vector space, is also a subspace when it is a vector space in the same operations that define the original vector space. And that's what the next definition says. And I would almost as soon not have to write it out, so let me, in case you don't have your book, there it is. Okay, back it off. There we go. I hope you can read it there. I know I'm moving a little bit. There is your definition of a subspace of a vector space. So let me describe to you what it is. It cannot be the empty set. Okay, that is out of it. So it's a non-empty set, a non-empty subset W of a vector space V okay, is a subspace of V when W itself is a vector space under the operations of addition and scalar multiplication that define V. So it doesn't have to be the standard ones, but it has to be whatever define the space V, those same operations of vector addition and scalar multiplication will have to define W, and it must fit every one of those 10 criteria. Okay, so here's example 1. This might seem a little bizarre at first, but it works. So let me clear the screen here. Anyone need this up any longer? Okay. Now, I keep losing my style. Oh, there it is. Okay. It's a black stylus and everything's dark in here and I can't see it when I set it down. Okay, here we go. Here is a set W. The set W, not necessarily a space, set W is, and it's a set, so it has the brackets there, all ordered triplets, okay, x sub 1, comma 0, comma x sub 3. Okay, where such that, oh, I'm sorry, I shouldn't have closed out the brace there. Set of all, because I'm not through with the definition, such that, that's what the colon there means, such that x sub 1 and x sub 3 are any real numbers. Yuck! Get out of there. Are any real numbers. Okay, sorry. My hand hits a button on this and then it goes back and erases something that I've just drawn. There, it erased the symbol there. Okay. So x1 and x3 are a set of all real numbers, or elements of real numbers. Okay. Now, show that that W is also a subspace that's going to stand for subspace of R3. Get out of there. Okay, subspace of R3 with the standard operations. Standard operations. Okay, I'll just end it there. Okay, now first thing you note, W is not an empty set, okay, because x1, x3 are any real number, so yeah, it's not an empty set. There is something in there, okay? That's the first thing. Now, one thing they note right off the top, it contains the 0 vector, because x1 and x3 could be any real number. 0 is a real number, so that would be 0, 0, 0 would be in that set. That's important because every vector in a vector space, no, let me rephrase that. In every vector space, there has to be a 0 vector. This one has it, so that's good. Okay. Now, side note here, time out. If that had been x sub 0, I mean x sub 1, comma 1, comma 3, that would not be, that would be a subset of R3, but it would not be a subspace for a couple of reasons. Number one, add any other vector to it, x sub 4, comma 1, comma x sub 5, and you're going to get a thing x of 1 plus x of 4. Hey, that's no problem. But 1 plus 1 would be 2. 2 would not be in this space because that space would be x of 1, 1, x of 3. It can't have a 2 in the middle. 0, no sweat. Add any vector with 0 in the middle and you still get 0 in the middle. Okay, so far that's a vector space. I mean, so far it's met all the thing. Closed under vector addition, has a 0 vector, it commutes, and it also associates because you always wind up with a 0 in the middle. Okay. Seems like we've hit them all there. When you do your standard operations of scalar multiplication, any c you multiply by that will give a cx1, 0, cx3. That's in the vector space. It's closed. It commutes. Oh no, they don't do commuting there. It distributes. Everything seems to work. It does contain the 0 vector. And guess what? 1 times this will produce x of 1, 0, x of 1, x of 3. So every one of those things fits. Okay? All right. So it is a vector space. Now, here's one reason it's a vector space, and this is given by the figure in the book. If your middle component is always 0, that means in space your y's are always 0. So that means you're in the xz plane. Well, guess what? The xz plane is R2, okay? You know, it's just that this definition here has a 0 in there instead of a blank. So if R2 was a vector space, so is this one, okay? Because you're talking about exactly the same deal here. Okay. Now, to establish that a set W is a vector space, you must verify all 10 axioms. Now, we didn't go through every one of them, but you could just see, thinking through them, they all work. Okay? If W is a non-empty subset of a larger vector space V, and the operations defined on W are the same as those for V, that's what we said before. However, then most of the 10 properties are inherited from the larger space and need no verification. So this next theorem cuts down your having to do all 10. Okay? And here's what that theorem says. I'll show it to you first, then I'll actually write it down. This is a theorem we're talking about right here. Okay? Now, this is worth writing down because this saves you from having to go back and do all 10. Because most of those others, like commutativity of addition and associativity of addition and those little associative things you have in multiplication with scalars and distributing scalars, most of those will come, like they said, inherited from the original space. If it's a subset of that original space, those are all going to come with it. But here's the thing. If W, didn't have my pad in front of me. I was trying to write on the keypad of the computer. If this W, a non-empty, and here's how I'm going to say this. The empty set is like this, so I'm going to say the non-empty set. Okay, that's negating a negation. Non-empty subset. And I think for subset from now on, I'm going to do this. That's the symbol for subset, okay, of a vector space. And for vector space, I'm going to put VS. And that vector space is, that should be a small vs, but vector space V. If that's the case, a non-empty subset of a vector space V, then W is a subspace, and SS will mean subspace of V. V is a vector space if and only if. Now this is the double-edged sword. If and only if the two closure conditions listed below hold. Okay? And here's what they are. First, if U and V are elements of W, then U plus V is also an element of W. That's the closure. It's kind of combining the first and second together. If you go back and look at those, the first one is, no, it is just the first one. U plus V is closed. Okay? The second one is basically the closure of scalar addition. If U is in W and C is any scalar, okay, then CU is the scalar product is also in W. If both of those hold, then the W is a subspace. You know it's a subset. They already told you that, of the vector space V. But if W obeys the closure under scalar addition, a vector addition, and the closure under scalar multiplication, then it's a vector space, a subspace of V. Okay. Now, the proof they do there is probably a pretty good proof for you to read through and follow. We don't have time to do it, but it's probably worth you taking a look at. Now, a subspace of a vector space is also a vector space. We've already said that. So it must contain the zero vector. That's usually a very easy thing to check whether you do this or not. Check first to see if the zero vector is there. If it's not there, it's a subset but not a subspace. Subspace has to have a zero vector. Okay? Now, in fact, the simplest subspace of a vector space is the one that only has one element. Okay, can't be an empty set, but it can have only one element as long as that element is the zero vector in that vector space. Okay, that is itself a subspace because that added to itself is in that space. Multiply C by it's in that space. Commutes, it does everything it's supposed to do. Okay. Now, another subspace of V is V itself. Okay, of course, if V is a vector space, it is a subset of itself, and of course, since it already was a vector space, it's still a vector space, so it's a subspace of itself too. Now, every vector space containing those two trivial subspaces, subspaces other than those are called proper or non-trivial subspaces. So the subspace that is only the zero vector is of course a subspace, but that's a trivial subspace. The space itself is a subspace of itself. That's a trivial subspace. Any other subspace that's not either the zero vector or the original subspace itself, then that's a proper subspace, okay, or non-trivial subspace. Boy, I'm getting dry. Let's see, we have about 45 minutes to go. Let me drink something. Wasn't much there. That's a little better. Okay. Let's do example 2. I don't know. I hope it's just the heating outside, but it's getting hot in this room. I've got the fan on and everything, but it's hotter than it normally is. Feels like anyway. Sorry about that. All right, here's example 2. Let W sometimes the pen writes and sometimes it doesn't. I don't know. And that's the set of all 2 by 2 symmetric matrices. I'm abbreviating like crazy. Okay. So W is a set of all 2 by 2 symmetric matrices. Now what we need to do is show that W is a subspace of the vector space M22, okay, with the standard operations abbreviating like crazy, that's operations of matrix addition and scalar multiplication. We're not making up any new rules here. Matrix addition and scalar multiplications. Okay. Now, you might need the little refresher that they give you here. A square matrix is symmetric when it is equal to its own transpose. That's what we mean by symmetric matrix. Now we're dealing with 2 by 2 symmetric matrices. And basically, let me get to the shortcut, okay? It doesn't matter what is on that main diagonal. Doesn't matter at all. It doesn't have to be ones and zeros. It doesn't matter. Just whatever is on there. What does matter is what's in the other spots. The main diagonal is just the 2, the first and the fourth. The other 2, 2 and 3, let's just call it that, they have to be the same. That's all that it does to be a 2 by 2 symmetric matrix. Okay? All right. All right. Now, obviously, the set of all 2 by 2 symmetric matrix W is a subset of M22, all 2 by 2 matrices. Okay, obviously that's a subset. So everything else is going to be okay. We just have to show that with your standard operations that are given here, that those are closed. So I'm going to represent every matrix in W this way. I don't know if this is how the book is going to do it, but this is how I do. This would be the matrix. I'm going to call it W1. I'll call it W11, W12, W12, because these two have to be the same W22, right? W1 and 11 and 22 can be anything in the world, doesn't matter. These two have to be the same. Okay, that's why I gave them the same representation. Okay, now maybe it would have been easier, and let me reconsider this and think, would this make more sense? I like this a little better. A, B, B, C. That's easier to write and it's easier to see, right? So let's say we take that one and add it to any other. Let's call it D, E, E, F. Okay, that's any other symmetric 2x2 matrix. Okay, now is this also a symmetric matrix? That's the first key. Let's see if it is. A plus D, nothing wrong with that. B plus E, nothing wrong with that. B plus E, everything's right about that because these two are the same. And then C plus F. All that's required here is this also is a symmetric matrix, and sure enough it is. It doesn't matter what the main diagonal is, these other two elements must be the same. Okay, and they are. So we've got the first part done. Scalar multiplication, vector multiplication, in this case vector addition, in this case matrix addition, is closed, because any two symmetric matrices you add together, you're going to get a symmetric matrix. The second part is if CW, any scalar C, times that matrix W, which I'll go back to calling A, B, B, C, this would be the matrix CA. Ooh, bad choice, bad choice. Make this D, okay? That's not the same letter there, okay? CA, CB, CB, CD. Is that a symmetric matrix? It doesn't matter what this is, these two have to be the same. Yes, it is. That's all you have to do to prove that this now not only is a subset, we knew it was a subset. It's a 2x2 matrix. The set of all 2x2 matrices, it certainly falls in there. Okay, so it's a subset. It's not an empty set, okay, because you can come up with lots of ones that aren't. And then also that it holds. Now, it's usually a good idea to just say, is 0, 0, 0, 0 also true? Yes, it is, because 0, 0, that's the 0 matrix. Is that also a symmetric matrix? Yes, it doesn't matter what this is, these two are the same. So yes, that's a symmetric matrix too. So this space, this set, has a 0 matrix in it, and it fits these two bills. Okay? Whew. That was example 2. I hate to do this, but I've got to go get some more water. I'm just so, my throat is so dry. Let me pause. Well, guess what? I can't pause my recording because it's not showing up on the screen. Started doing that some. I'll be right back. It won't take me long. Okay, sorry about that. I just had to have something else to drink. Now, the problem with doing that, I've got to get better at this. I can't find now where I set the stylus. There it is. Again, it's black on a dark surface. Okay, that was example 2. Did that make sense to you? Good. Okay, let's move on to example 3 then. It says here, let me go on. Can I clear the screen? All right. Example 3, let W, we're going to start here. Again, this is a situation you might think, well, goodness, would any subset be a subspace? The answer is no. Okay, we know that. Let W be the set of singular matrices of order 2. Okay, the set of singular matrices of order 2. Now, that means they're 2 by 2 matrices. That's a subset, of course. Now here's a subset of M22, because set of all matrices that are 2 by 2 matrices, certainly singular matrices that are 2 by 2 would be that. So that's fine too. With the standard operations, okay. So we're not coming up with anything wacko here with standard operations. Okay. Now, do you remember what we mean by singular matrices? That was what I was worried. Last time they reminded you what a symmetric matrix was, but here they're not reminding you what a singular matrix is. Okay? Now, anyone want to hazard a guess what makes up a singular matrix? I'm about to drop my pen. Okay. A singular matrix is one whose, I guess there's lots of ways to say it, but to me the easiest way, especially since we're dealing with order 2 matrices, one whose determinant is 0, right? If it's not 0, it's not singular. Yeah. So singular means not invertible. That's what singular means. So it's obviously got to be a square matrix, otherwise we won't even talk about it. But it's a 2 by 2 matrix, not invertible. So the easiest way to think of that, it's, in my mind, being a 2 by 2, it's just its determinant is 0. Okay. So let's just come up with 2 matrices whose determinant is 0. And you can come up with any 2 you want to, but give me one. Give me one matrix that would be in W1. Okay? Give me a number. Make up a number. 2. Another one. 8. Another one. 1. I'll tell you what this one has to be. Anyone know? 4. Absolutely. Because its determinant is going to be 0. Okay, I want you to make up another singular matrix. We'll call it W2. Make up another one. Okay. Very nice. And that has to be 2, right? Okay. Now, remember that what one of the properties is that if you add these two matrices together, you better come up with another singular matrix, right? So let's see if we do. The sum of these two, and if you've given me one it just happens to work, I'm going to disavow knowing you. Okay, let's just add these two together. 2 plus 1 is 3. 8 plus negative 2 is 6. 1 plus negative 1 is, and 4 plus 2 is, you think that's a non-singular matrix? I mean, it's a singular matrix? That is non-singular. This is invertible, not singular. So obviously this set of singular matrices is not a subspace. It is a subset of 2 by 2 matrices, but it's not a subspace of 2 by 2 matrices, because the simple rule of matrix addition does not produce another singular matrix. Okay? Good deal. The book did a sort of easier one. They did 1 0 0 0 and 0 0 1 0. Okay? They were really lazy, weren't they? Okay. You're a nice hardworking people. Okay. Now, here's an example 4. Let's go on and hit this. You have now passed where we got to last spring, but that's not saying a lot. But it is. It is nice that you go past that. So let me clear the drawings here. Let's do example 4. Okay. Here is W. Okay. A new W here. And they don't tell you what it is, they just write it out for you. W is the set of all ordered pairs x1, x2, such that x sub 1 is greater than or equal to 0, and x sub 2 is greater than or equal to 0. Okay? There is a set of ordered pairs with x1 greater than or equal to 0 and x2 greater than or equal to 0. And my thing just fell off my pocket. Hold on just a minute. This has gotten to be somewhat of a pain in the neck. Why is it getting twisted like that? I don't know. Okay. Now, I want to suggest something to you. Certainly, this is a subset of R2. Remember, R2 is a set of all ordered pairs. All ordered pairs. This is a set of ordered pairs, x1, x2, but these are all non-negative elements in that. Okay? Now, certainly a subset, so the 8 of those 10 requirements are met. Just being a subset of R2, they're met. The only 2 that you have to prove is the vector addition. In this case, it truly is ordered pair addition. So if you were to add any x1, x2 to any other x3, x4, as long as both of these are non-negative numbers, all of those are non-negative numbers, do you get your result x1 plus x3, comma, x2. Goodness, my phone keeps ringing off the hook this morning. I'm in class. I'm not answering a phone. Okay, plus x4. It just keeps ringing. Okay, is that also, are those both of those non-negative numbers? Of course they are. If x1 is not negative and x3 is not negative, add them together, they definitely can't come up being negative. If x2 is not negative, x4 is not negative, definitely the sum is not negative. So it fits. It meets the requirement for your vector addition. Okay, it's closed into this for this subset. But the one that isn't, remember the other one, that for any c, scalar c times x1, x2, that also has to be in the set. Well, all you have to do is come up with one example where it wouldn't be. How about if c was equal to, remember it's any scalar, if c is equal to good old -1, then this would be negative x1 comma negative x2. And guess what? If x1 is greater than 0, negative x1 is less than 0. If x2 is greater than 0, negative x2 is less than 0. Guess what? That doesn't fit the bill for scalar. It doesn't fit for your standard operation of scalar multiplication. Does not work if your scalar is negative. And remember, scalar multiplication for any scalar number c. Doesn't have to be positive, doesn't have to be negative, any one. So this is why that one doesn't work. Does that make sense? All right, good deal. I kept it general. They used the vector 1, 1, which is certainly NW, and then multiply it by -1, which is what I did, and you got -1, -1, which is not NW, so it's not closed in scalar multiplication. Now, this next example I find is neat, okay, to look at. I'll clear all these drawings out of the way, and I really just as soon not write it out. I'd rather look at the picture. But let's see, I might need to write it out for you too. Okay? Let's let W5, okay, starting with W5, be the vector space, and I already tell you it's a vector space, of all the functions defined between 0 and 1. All the functions defined between 0 and 1. That your independent variable, let's just call it x, is between 0 and 1. So W5 is a vector space of all functions defined from 0 to 1, including 0 and including 1. Okay, that would not include 1 over x, because 0 is included there. Okay, it would not include 1 over 1 minus x either. That would be. But any function that's defined on that interval, 0 to 1. Now, let W1, and here's how they're going to define that. The set of all polynomial functions defined on 0 to 1. Well, guess what? A polynomial function is a function, so obviously that's in your first set, W5. Okay? W2 is a set of all functions that are differentiable on 0 to 1. Now remember what differentiable means. To be differentiable, the function has to be smooth and continuous. Guaranteed all polynomial functions are smooth and continuous, but there's other smooth and continuous functions that are not polynomial. For instance, the sine function. Okay, it's not a polynomial function, but it's still differentiable. Okay? Okay, I sort of gave something away there. Sorry. W2 is a set of all functions that are differentiable on 0 to 1. Oh yeah, it's fine. Okay. Then let W3 be the set of all functions that are continuous on 0 to 1. Okay, now the only difference here is they don't have to be smooth. They just need to be continuous. So if you had something that looked like an absolute value function that's defined on 0 to 1, then that would be smooth. I mean, that would be continuous, but not differentiable. Okay? If that v showed up on there. But it's still a function defined on 0 to 1. And then W4 is a set of all functions that are integrable on 0 to 1. Okay, now wait a moment here. You can integrate piecewise. So if you have a function here that between 0 and 1 does, say 0 to 1/2 does this, at 1/2 it does this, as long as it's defined everywhere there, it is integrable, but it's not continuous. Okay, and that certainly would be a subset of all functions defined on 0 to 1. Okay, so basically what they're saying is W1, set of all polynomial functions, is a subset of all differentiable functions. That's a subset of all continuous functions. That's a subset of all integrable functions. And that, of course, is a subset of all functions, period, whether they're integrable or not. Okay? Now, what you're asked to do is to show that every one of those subsets is also a subspace. Now, all that's required, remember, is that it must meet the addition criteria and it must meet the scalar multiplication criteria. Well, set of all polynomial functions, they certainly meet addition and scalar multiplication. No doubt about it. Okay? Now, set of all differentiable functions, yeah, that rule is in differentiability. I mean, that's one of the first things you say about it, that if f and g are both differentiable, then the derivative of f plus g is f prime plus g prime. They're both differentiable, yeah, that works. Continuous functions, yeah, there's no, oh yeah, scalar multiplication, yeah, that's also, if f is differentiable, c times f of f is differentiable. Okay? Continuous functions. If you add two continuous functions together, there's no way you can introduce a discontinuity there. No way whatsoever. So therefore they are, that's continuous. That addition. And when you multiply a continuous function by a constant, any constant, it remains continuous. Okay? Integral, yeah, same deal. So they are also all subspaces. Okay. Now, I like their graphic. That's the one thing I really like about this. All your polynomial functions are subsets of all your differentiable functions. All your differentiable functions are subsets of continuous functions. All your continuous functions are subsets of integrable functions, and all those are subsets of all functions. Okay, and since all those are spaces, well, you can't say because they're subsets they are, but they're also subspaces. That it work if they're all subspaces, you could draw the same diagram, but that diagram really only represents subspaces. Okay. Now, theorem 4.6. The intersection, okay, now do y'all remember intersections? Do you remember Venn diagrams? Now this is sort of a Venn diagram we just showed, but in Venn diagram, if this represents the space and that represents the space, or sets anyway, this is the intersection of those two spaces. Now, so here's what theorem 4.6 says. The intersection of two subspaces is also a subspace. Not just that the intersection of two subsets is a subset. Yeah, that's obviously true. But would it be that the intersection of two subspaces must also be a subspace? So basically it's saying if this is V and this is W, and they're both subspaces of your universal set, which if I could get my pen, ooh, there it is. Okay, this is ugly. I'm drawing off to the side here. This is U, your universal set. If they're both subspaces of a vector space U. Now all these are vector spaces. Then it says the intersection of V and U, and by the way to represent that in math speak is V intersect W, is also not just a subset but also a subspace. Okay. Now, what would have to be proven here, certainly you already know they're subsets. We know that by basically our Venn diagram here. But can you guarantee that for any element of V that is in this part and element of W that is in that part, when you add them together, you don't produce one that's somewhere else? Okay, in other words, here or here. Yes, you would have to. Well, wait. Yeah. Okay. And here's why. Okay. If it's in here, element of V in here, and it's an element of W that's in here. Okay. So let's say there's two different ones of them. Here's one. Let's call it UV. Let's call it T. Let's call it a U. No, we already used. Let's call it a T. Little t1 and a little t2. Okay. Now, little t1 and little t2 are both in V and in W. They got to be. If you were to add those together, can you guarantee that you're still in there? Okay. Well, since T1 and T2 are both in V, you know they both got to be inside this big one. The sum of them has to be inside V, inside the big. Why is my pen not agreeing with? There it is. Okay. The sum of them have to be in here, but since they're both in W2, the sum has to be in here as well. And the only way that it can be in yuck in this one and in this one is if they're in the intersection. And if you were to multiply any old scalar times C and that same scalar C times T2, then have you gone outside? Well, the same argument holds. If C times T1, you know, has to be somewhere in V because that's a vector space, but it also C times T1 or T2, it doesn't matter which, also has to be in W, and the only way it can be both in V and in W would be in the intersection. So yes, that subspace, that subset that is the intersection of two subspaces, also is a subspace. Okay. Now they kind of did the same thing I did, I assume. Okay. And that they used the Venn diagram. Their U was circular as well. I did a rectangular. It doesn't matter. All right. Let's move on to the next one. Subspaces of Rn. Oh, and by the way, I'll I'll show you their Venn diagram. They used U as a circle, but they did the same thing for V and W, and the intersection V intersect W, just like I did, and I think their proof follows pretty much what I said. Okay, now subspaces of Rn. Rn is a convenient source for examples of vector spaces, so the remainder of this section is devoted to looking at subspaces of Rn. And here will be the first one. Let's see if I can clear the screen, because that took too much room. Alright, determine whether each subset is also a subspace of R2. We're going to only deal with R2. Okay? The first of these is the set of all points on the line. I should have written this set of all x1 or xy's. Let me just do xy's on the line x plus 2y. I can't write. Is equal to 0. Okay? Determine whether each subset is a subspace of R2. Set of all points on the line x plus 2y is equal to 0. Okay? Now, is that it's certainly a subset of R2. It's an ordered pair, x, y. Okay, subset of R2. Is this, the question is this a subspace of R2? R2, I'm putting my question mark. Is it a subspace of R2? Okay. Now, remember what's required? For any two values that would make that true, x, let's call it x1 plus 2y1, we know is equal to 0, and we also know that x2 plus 2y2 is equal to 0. Does that guarantee the sum is also equal to 0? Well, that would be x1 plus x2 plus 2 times y1 plus y2. Is that also equal to 0? Well, add them together and see. 0 plus 0 is 0. Yes, it would have to be. Well, that's this vector multiplication, vector addition part. How about scalar multiplication? Can you take any old c, multiply it by this? Would that give you 0? Yes, it would. Okay, so guess what? That first one is a subspace. The answer here is yes. Yeah, get out of there. Okay, the answer there is yes. I tried to put a check mark there and it didn't work. That one does work. Okay, now the second one is a set of all xy points such that x plus 2y is equal to 1. Okay? Is that a subset of R2? That's the question here. Is it a subset? Okay. And without doing anything else, I would suggest to you the answer is no. Can anyone think of why? I didn't do it up here because you had to show more than this. But for in general, this works. Okay. But here I can pick one example and say it doesn't work. And that one example is, remember, to be a subspace, it has to have the 0 vector. And if you put 0 plus 2 times 0, do you get 1? Can you possibly get 1? No, you can't. You cannot do it. So the 0 vector is not in this space, so therefore it's not a subspace. Every space has to have a 0 vector. This one does not. The top one did. Put a 0 in for x and y, and sure, you get 0. Doesn't matter what the 2 is or anything else is, it does contain the 0 vector. This one does not. Okay? So that was a pretty easy one. Okay. We're down to 1 minute, and I doubt if I can get much done in a minute. So let's pause here. Let me get my pencil in place. And we'll start next time on page 171 in section 4.3. And like I first just said, you have now passed where we got to in the spring, but that is not necessarily an admirable thing, but you got further than we did in the spring. Okay, 4.3 homework exercises. Do any of the odds 1 through 5. Any of the odds, and they're all at calcchat.com. They're also in the back of the book, but you can see the worked out solutions at CalcChat. Any of the odds 7 through 19. Any of the odds 21 to 27. Any of the odds 29 to 35. And hold off, we'll pick up the rest of those next time, okay? All right, good deal. Now, let me just give you a hint, okay? I know a lot of you have been turning in homework work, and I appreciate that. I really appreciate it. But from now on, I'd rather you turn in tests, okay, or research papers or something. Remember, all you have to do is turn in something every week, okay? And we only got this week and next week left. The final's got to be turned in for next week. For this week, okay, all you have to do is turn in something. So if there is a research paper you haven't done yet, be sure to get that in. If the test 1 you haven't turned in yet, be sure you get that done. If there's test 2 you haven't turned in yet, be sure you get that turned in. Or test 3, if you haven't turned that in, get that in. Don't worry about turning in some homework exercises if you're going to be turning in a test or a research paper this week. So get that to me. That's the more important. And then next week will be anything else you want to turn in plus that final exam. So don't sweat about specific homework problems in 4.3. I'd rather have your other work to come in. Is that all right? It may be easier to turn in this homework. I don't care about easy. I need the other stuff in. Spend your time on that. Do the homework, but don't worry about sending it to me. Get me something else, anything else. All right, I just went a minute over, but guess what? There'll be no extra charge. Okay, so I'm going to stop the sharing. Any final questions, thoughts, issues, concerns, clarifications, anything? I take it not. Good to see perfect attendance today. Keep it up all next week, and we'll be through, folks. So if I don't hear anything else, I'm going to end the meeting for everybody. Bye-bye. See you on Tuesday. Have a good weekend. Working on linear algebra will make it good, right? Good deal.